Right. Hello, everyone. My name is Revi, and today we're going to be talking about an introduction to the process industry. Hope you all can hear me. Let's get started. Let's go right into the introductions. Give that a second to load. And yes, we run from the top. Penny, over to you.
Hello, can you hear me?
Yeah, all clear.
Hopefully. Yeah, okay. Hi, I'm Penny, and I am a project engineer at Koolmill, and I'm also a member of the Food and Drink Committee.
Pam?
Hello, thank you for that. Pamela Robinson, I'm a member of the Water and Wastewater TAC committee. I am also a principal engineer in Atkins, and I work in the water and wastewater sector.
Thanks. Masood?
Yes, good morning. This is Masood Bagarzadeh. I'm the engineering manager at Fleur, and also I'm a member of the process industry board in IMechE.
Yeah, and as mentioned, I'm Renaissance McGrelly, or Revi for short, but I have no discernible titles after my name just yet. Maurice?
Yeah, Maurice. I'm a member of the Pharmaceuticals Technical Activity Committee and Vice Chair of the Northwest Process Division. I was previously a long-term employee of a US pharmaceutical company.
And John?
Good morning, John Bartlett. I am with Maurice, the Vice Chair of the Northwest Centre. I've worked in ICI, MOD, UKAA, mainly nuclear, and then regulator for HSE of nuclear, again, chemical business. Thanks.
Lovely, thanks, John. Before I forget, folks, if you have a question through the presentation, please use the, I think it's Ask a Question box, and it should come through to us, and we'll run through them at the end. Right, over to the next slide. So I'll start with some background to the process industry. So, yeah, the process industry concerns itself with the continuous production or batch production, where each batch is identical. So, for example, in the bottom right there, it's orange juice, maybe drink, probably not a juice. It might have come through a continuous or batch process, but each bottle of orange juice is the same. This would differ for something like automotive, where you have almost discrete manufacturing. You have bills of materials, you have assembly of components, and each car rolling off the shelf can be different paint, different wheels, and what have you. We cover many different business segments, including food, pharma, oil and gas, petrochem, and water. So the representatives we have today and a little more as well. So scale of facilities, what do we deal with? It could be something small, small for us, yeah, about 50 grand. So that's perhaps a small pumping station as part of a wastewater treatment, or it could be $100 billion US, and that would represent the entire investment through the life of an oil field. And again, I say entire investment, it's a lifetime investment, it's not one upfront thing. It's the GDP of several countries. So, yeah, it's an enormous breadth and sense of scale here. Footprint-wise, again, we can go small to big. So small, I would argue this little homebrew setup from Alfa Laval constitutes a process plant, if you will. You have process piping, you have process equipment, you've got pumps, heat exchangers, perhaps a cyclone. You'll have utility connections to your mains water, to drainage, if you will, electricity. So it can be that size. Or on the right, that's Das Island. That is an island in the Persian Gulf, man-made island, dedicated to the production of oil and gas. It is enormous. If you see that flat strip diagonally on the right there, that's a runway for the planes. And those large tanks could easily be 100 meters in diameter. So again, when we talk footprint, we go small to big as well. And yeah, I'll now pass to Penny, who will speak a little about food and drink industry.
Hello, hopefully you can hear me. So let's go on to the next slide. Yeah, there we go. So food and drink unites the world and powers us forward. Our bodies simply need it to stay alive. On average, we eat 3 meals a day and we drink between 6 to 8 cups of fluid a day. In the UK, we eat food and drink that is grown or produced in countries all over the world, and it travels miles before it reaches your plate. But have you ever stopped to actually think about how these products magically appear ready to be cooked or eaten in our supermarkets? So the food and drink processing sector transforms raw agriculture commodities or semi-processed food products into a broad range of semi-prepared or consumer-ready food and beverage products. So on this slide here, you can see a woman on the left picking paddy, which, as you can see on the right, once processed is what we all know and love and recognise to be rice. It's this process that Koolmill, the company where I work, specialises in. So at Koolmill, we effectively sand rice. We have created a modern, ultra-low power, simplified and sustainable approach to cereal milling. The machine on the right is the Koolmill machine. And as you can see here, there are 3 different ways that rice can be and still is processed today all around the world. So on the left, you can see hand pounding, which still happens in places in Africa and particularly in Malawi. And so women can spend 6 hours a day hand pounding rice. So they're essentially smashing the paddy, the husk, into white rice, which is what we eat. Then in the middle, you have mechanized milling, which was introduced in the 1860s. But this way of milling is they use a lot of heat, and it's very mechanical heavy, let's say, and it can result in losses of up to 80% in the entire production. So you're losing and you're damaging a lot of the rice along the way. And then Koolmill, after 8,000 years, is the 3rd generation of this technology. We really are bringing about something completely different and changing the game. We work with cold milling, and our machine can also run off grid because it is so low powered. So yeah, we're basically looking at trying to really maximize the return of food and to avoid wasted rice and power. We also are carrying out some research so that we can utilize the whole rice plant, which is something that I've been working on the past year that I joined the company. And we're looking at, so you get bran, which is a byproduct from processing rice, and this can be converted into nutritious human food ingredient. And also we can use the husk to be burnt for power as well. So in my day-to-day as a project engineer, I do a range of activities. I'd go from testing and carrying out milling trials, which involves the joyous task of counting rice by hand, which I've learned, and then also to organising the team and managing finances, for example. So it just gives you a bit of an idea of what a project engineer does in the food and drink industry. Now, I chose to enter this industry because I really recognise the positive impact and potentially life-changing effects technology can have on people. And to be honest, I really never knew much about the food and drinks processing sector before joining. But from working in places like India and China during university, I observed how different cultures and countries' processes sell and eat food, like how much of an impact they can have on someone's life. In the UK, we are so fortunate. We either import food and drink that's already been processed and packaged in country, or we use our own advanced food and drink processing systems based here in the UK. So, for example, in Scotland, we have the fastest bottling line in Europe based at Highland Spring in Blackford, which some of you may know bottles spring water to sell around the globe. The Highland Spring line makes and fills 73,600 bottles of water every hour. So just to give you an idea of the scale. Now, from growing up watching how it's made, I think one of the best ways that you can find out more about the sector is by watching videos. So I've got one here, which is from inside the factory, and it just shows how a poppadom is made, and Greg Wallace explains the technology much better than I can, so make sure to listen up.
I love robots. They are magnificent. How are they picking them up?
The working air pressure. Suck them up, lift them, put them down.
The factory uses a staggering 500,000 of these raw poppadoms every day. More than 130 million a year. Is that it?
That's it now. Shut the door.
The raw poppadoms are carried on a conveyor belt into an enormous 5-metre-long fryer. Inside, they are cooked in 1,300 litres of rapeseed oil at 170 degrees C. How long do the poppadoms take to go through there?
10 seconds from one side to the other.
When I do poppadoms at home, you put them into the oil, and they puff right up. How do they travel through there? Do they just float?
No, they're sandwiched between two belts to keep them flat so we can pack them.
Is that it?
That's it.
Now 30% bigger, the cooked poppadoms fly out of the fryer at a rate of 6 per second and have any excess cooking oil removed.
We blow air on them to blow the oil away.
What is that glowing red tunnel of love?
That is magic.
More science fact than magical mystery. Light sensors in the roof map the position of each poppadom and pass the information onto the packing robots. That is like some sort of demented chicken. These robotic heads suck up the poppadoms using a vacuum that is just strong enough to lift them without snapping them. Any they miss are picked up by the next one. How did that is the quicker, that is so fast. What does it remind you of? To me, it's a chicken.
It's a crazy chicken.
It's a crazy chicken, isn't it?
Crazy chicken.
It really is.
Okay, so, sorry, can you guys hear me? Yeah? So hopefully from that video, and I'm just going to talk over this video as it plays right now, you can really see the vast array of different engineering technologies which are used in the food and drink processing sector. So even for the simpling actions such as rinsing these beer cans out before filling, you've got to ensure there's no dust inside. And then also, for example, laying the lids on top of the can requires these processes, which seem so simple to us, require complex mechanical engineering design. And yeah, so one thing which really fascinated me was when you're designing or improving processes on the scale, you have to take into consideration lots of different things which I maybe didn't think about through university. Was, for example, quality management, so ensuring that each beer tastes the same and it's got the exact same amount of liquid inside that's advertised on the can. Then you've got health and safety, so ensuring anyone operating the machines isn't injured. Cost reduction, for example, if you reduce the amount of aluminium needed for each can, even just by a micromillimeter, that could save the company millions in return. And then in time is another one. So time is money in the processing industry. If you can reduce the time it takes for the beer can to go from the start of the line to the end, it means you can produce and package more beer cans between the working hours of the factory. Yeah, so if you like this, oh here, that's quite a cool video of the lids just going on, which I was explaining earlier. And then finally, because that video is too long to play fully, but finally, there exists a huge opportunity in the food and drinks processing sector, which is one of the reasons I got into it. The question we should really all be asking ourselves as the innovators of tomorrow is, how can we make globally secure food systems that are sustainable and help reduce poverty? So during the past year, COVID-19 and Brexit have revealed how vulnerable our food systems are. relying on imported food exposes a country to limited supply. Or, for example, how we're experiencing today in the UK, we have no petrol for our cars. We also have a growing population and climate change to think about. So let's just take rice industry, for example. Currently, the rice feeds 3.5 billion people daily, but by 2050, this will be 6 billion, and production will have to increase by 70% to meet demand. And then on the climate change front, rice is also a major polluter. It's responsible for around 2.5% of all greenhouse gas emissions, and the rice's climate footprint is comparable to that of international aviation. So therefore, it opened my eyes and it made me realize that we've got to make better use and process better what is already growing. Growing more rice is no longer a viable option. So these problems of climate change, a growing population and insecure food systems are applicable to more than just the rice industry. They're applicable across the whole of the food and drinks processing industry. So here really exists an opportunity for any of you guys listening to solve. Yeah, thank you for listening.
Thanks for that, Penny. Yeah, over to you, Masood.
Thank you, Rebbe. Can you hear me?
Yeah, all good, all clear.
Well, thank you. Yes, so I will be speaking about oil and gas and chemicals industry, or as I prefer to call them, energy and chemicals industry. The energy and chemicals industries are covering a broad range of process industries, which traditionally included mainly oil and gas. But it also includes likes of LNG, hydrogen, carbon capture, and also very important is the chemicals we produce. So the photos you see on the screen, they may look very similar, but in reality they are a different type of plants which are producing different type of fuel or chemicals for us. So historically, oil and gas projects have been dominant in the energy industry, but there's always new and emerging technologies, which recently are like LNG, hydrogen, carbon capture. They're all gathering momentum, and they will all support reducing the greenhouse emissions, as well as serving our energy needs. On top of that, chemicals form a significant portion of the industry and provide us with the material that can help advance our other technologies. So the products from chemicals are used everywhere, from packaging, say food, to mobile phones, computers, and also even in the spacecraft, because they come in very different shape and form and strength. So there's always a huge potential for mechanical engineering in these industries. You can be a design engineer designing any of those equipment you see on the screen, or it could be laying out the plant, could be all sort of design activities, or it could be engineering management and project management, and also construction. Ultimately, we have to build these plants. Energy industry overall has always been a very diverse and international industry, and we are always part of a multi-discipline, multinational, multi-location team. We always have teams in different locations. We're working with them, and also, as I said, and what my colleagues are, it's a very international business. So if you want to be part of the movement for greener future, and also in chemical industry, this is the industry to work for. So if you want to know about the products that come out of these plants, so let's move to the next slide. So the products typical, it comes in three different forms. They might be liquids, it's like petrol or diesel we use for cars. It could be gas, which is again could be the gas to our homes, or also a gas that feeds chemical plants, or being hydrogen being a gas. But also comes in a shape of solids, mainly chemicals, in particular polymers come in solids, although some of the chemicals are in the shape of gas or liquid as well. Some of the products you may be very familiar with, as I said, like petrol, gas in particular. But when it comes to chemicals, they may not be very familiar because they typically serve other businesses, not directly to the customers and users, which then the businesses make the products that then you will be familiar with. Examples of those chemicals are like polyethylene, propylene, styrene, polyvinyl chlorides, ABS, and all different type of chemicals and plastics and high strength material, which as I said, that we can use them all in all different industries. With that, I hand over to Pamela to talk about water and waste industry.
Thank you. Just unmuting myself there. Yes, I'm Pamela Robinson. I gave a brief introduction at the start, and I worked for Atkins as Principal Mechanical Engineer in the water and wastewater sector predominantly. On to the next slide. This just gives you two typical examples of the clean and wastewater processes that you could possibly find. It's not at every site. Every site is slightly unique, slightly different. The clean water example at the bottom, this is taken from a reservoir or a river abstraction, generally pumping stations, there's some settlement, some filtration, generally always disinfection process on the water side, which is generally chlorine. On this one, you've then got a huge tank held up in the air, which provides the pressure to deliver clean and wholesome water to your tap, whether that be in the industry or at your homes. Or there could be more pumping stations along the way to make sure that if you're at the end of the clean water network, you still get a suitable amount of pressure at your tap rather than just a dribble. This is just a typical example. If you were taking water from a aquifer, you could just have a borehole pump and disinfection, and it's wholesome enough to be able to deliver straight to your taps at that point, and there isn't the need for any extra processing. This is why water tastes very regional, because of where the source has come from and what's needed to be done to it to make it wholesome, so it doesn't make us ill. Obviously, water and wastewater is used in the UK and all over the world. So this could take you all over the world, this particular industry, if you want it to. Over on the right is just another typical example. It's not every wastewater treatment works. It's very unique for every wastewater treatment works. All depends on what foul flow is coming into the works and how it's to be processed. This particular example uses preliminary treatment of screenings and some grit removal. It then goes on to a primary settlement stage where the sludge is drawn off, the effluent weighs over. You then have some secondary treatment where the bugs are there to eat the nastiness out of the effluent. Then it's gone on to some further secondary settlement where some further sludges are drawn off and the effluent weighs over, and there's a final polishing stage in this particular example of some extra filtration before it's then deemed safe enough to go into the local watercourse. The effluent that's discharged is monitored to make sure it's to the right quality and the right quantity. We're not sending too much and we're not sending too little. The quality will depend on the watercourse that it's being discharged to. Again, every discharge is different. The sludges on the wastewater treatment works, that's where it gets a little bit more interesting. As the sludges I mentioned earlier are drawn off the process, the sludges can be used to create energy. So this is a very good energy from waste example, quite raw. The sludges are drawn off, they're heated up, the gases, methane is drawn off. The gas could be cleaned up and put straight back into our gas network, powering our homes, powering our industries, powering the site it came from. Or the gas could be used to drive engines, and the electricity that's generated could again be put it back into our network to power our homes, power our industries, and power the site that it came from in the first place. So it's very exciting that we're using our waste streams to create energy, to try and reduce our carbon footprint, to try and be better for the environment, to be more sustainable. Our sites are a working asset, a very real asset that you see up and down the country and all around the world. These assets have to be maintained, they have to be optimised, they have to be, the effluent, the discharge could change, we could have more houses built. So they always need to be modified. You may need to put extra assets inside that existing site to try and make the effluent suitable for the discharge, to deliver more clean water to homes. And then finally, when the asset reaches the end of its life, it needs to be decommissioned. We need engineers all across these stages. And we need you. We definitely need more engineers. And I find that the water and wastewater sector is quite an interesting topic to be part of, especially when we're talking about energy from waste. I think on to the next slide, if I get the right mouse. So this is just two examples that are actually happening at the moment. They're both wastewater treatment works. I'm sorry, I find wastewater slightly more interesting than clean water, but both have their place. On the left-hand side, this is a new site that's in construction at the moment. It's still being tested and commissioned. This is just partway through construction. I think it's being tested for water tightness when the picture was taken, and it's just being filled at the moment. It's not quite to its full capacity. And basically, it's a brand new wastewater treatment works. The existing wastewater treatment works, unfortunately, is due to coastal erosion, is disappearing faster than anticipated. So this new wastewater treatment works has been is a mile further in line and is outside of the coastal erosion 100-year plan. The flow comes in, so this is the left-hand picture, sorry. The flow comes in on the bottom right-hand corner. It's pumped in. So there's an upgrade to the existing pumping station that feeds this works to get it to the new site. It then goes round in a loop. On top of those lagoons, there'll be some aerovac units, they're called, which are basically wind-powered aeration systems, paddles below the water surface that keep the bugs alive, keep everything momentum, keep the wastewater flowing through the system. There'll also be aeration supplemented with diffusers, so there'll be some low energy blowers mounted at surface level between the two lagoons. It's then piped through to the second lagoon on the left, gone through with some more biological treatment with the form of the diffusers and the aerovac units with the paddle aerator systems, as I mentioned earlier, and it leaves the site from the bottom left hand side where there's some screens, and it's then either pumped or gravity fed to the long sea outfall, depending on whether the sea is in or out as to whether the pumps are required or not. This is a very low carbon solution. It's also massive. So we have to have the land available to be able to deliver this kind of system. This will be the largest in the UK once it's up and running as well. There are some in the Anglian area and some in Scottish water at the moment, I believe. And this picture is taken from the Yorkshire area. So that'll be brilliant. It'll be closely monitored as well as to how well it's doing, how the effluent quality is from the back end. There is scope in there to add in a UV unit if the effluent quality doesn't quite meet the standards set by the EA. But hopefully it will do, and it will be fine. It's a very low carbon solution as it stands. the site, the picture on the right is just a computer image at the moment. It's going through design. It's a wetland system, basically, to try and this AMP period, the wastewater and water sector work in 5-year work periods, and this 5-year work period, a lot of phosphorus, a lot of emphasis is placed on removal of phosphorus within our wastewater treatment works on the final effluent. And this is using a very traditional, I suppose, going back to what we possibly saw earlier, many hundreds of years ago, is wetland systems. So the buildings on the left, you can just see, contain some upfront screening, and then it cascades through the wetland system. This is the size of, I think, 3 Olympic swimming pools, yes. And they're hoping with this system, it will move the phosphorus as per the discharge consent. It will boost local wildlife. It's a natural way to remove phosphorus. It's sustainable, and it's certainly a low carbon solution. But again, a lot of land is required to deliver this. In many sites, we've already got the existing wastewater treatment works, and we're trying to make those assets work harder. So we may put in existing additional assets between existing assets to try and polish the effluent to remove that extra phosphorus. And we may not have the same land availability as we have with these 2 sites, but I just wanted to show you 2 low carbon solutions that are actually ongoing this AMP and very real. And just to stress again, we need engineers to help design, to help construct, to help optimize, to help decommission. We need engineers throughout the whole of this process to help make our world go around, to help deliver wholesome water and to treat our final effluent. Thank you. I shall now hand over to Maurice, who will discuss pharmaceutical. Thank you.
Thanks, Pamela. I'm going to talk about the role of mechanical engineers in the pharmaceutical industries. And the question is, you're a mechanical engineer, why would you want to come into the pharmaceutical industry? Well, the pharmaceutical industry is dedicated to improve people's lives, quality of life. It's got high standards and values. Pharmaceutical companies develop and make drugs that are dispensed into liquids, tablets, capsules, vials, syringes, and inhalers. All this is carried out in clean rooms using clean utilities and high quality machines that need high quality engineers to specify and maintain and look after them. You cannot make pharmaceutical products without engineers. And the pharmaceutical companies develop the contribution to engineers to make their products. Scientists start the process, but the engineers finish it. Now, to give you some idea of the scale, a cost of a new drug development from concept to approval, FDA, MHRA approval, is $1.3 billion US. That's one drug. And it may take 10 years. Not in the case of COVID, for instance. A new pharmaceutical facility costs between 10 million and 550 million US. Pharmaceuticals are highly regulated industry. The concept is you cannot quality test pharmaceuticals as you can in engineering. You can't take something off the line and test it. Quality has to be built in. In other words, when it's finished, it's right, first time, all the time. That's the product strength, the identity, the effectiveness, labeling, repeatability, thousands or millions of doses. There's no room for error. And this calls for highly disciplined engineers. And the engineers are used to working to tight specifications that control using approved drawings, etc., etc. The facilities have to be well designed, so the operations carried out using controlled temperature and humidity conditions in clean rooms. the rooms have to be designed so the operators are comfortable and they don't make mistakes. You know, they've got plenty of room to move around, and they know where to go and start things. There's a picture of I think it's a sort of a mini fermenter there, and that's an agitator. As you can see, a lot of stainless steel used. Just go back. Go to engineering practice. The engineering procedures have to be written down precisely so they satisfy the regulators. And all these procedures have a direct impact on quality. And the sort of GEP, good engineering practice, technical activity, specification, design, construction, operation, maintenance and repair of facilities and equipment, covering project management, qualification, commissioning, validation, calibration and testing, and documentation and record keeping, staff education, and contamination and environmental control. And I'll give an example of that. If an FDA, Federal Drug Administration inspector comes in, he would want to know part, say a start in a bulk production. He wants to know about the ticket that shows how much is going to be added. Then he would want to know about the machine that's weighing the product. Then he wants to know the calibration certificates of the machine. Then he wants to see the record, the training of the person who's calibrated the machine. In other words, it goes on and on and on. So no room for error. Now, the kind of jobs for mechanical engineers in the pharmaceutical industry, plant and equipment design, that includes all the design, specification of all the machinery, all the reactors, the vessels, centrifuges, etc. Then there's the plant operation, maintenance, reliability. That's ensuring that the plant is working correctly and it's maintained and it's reliable. Plant integrity insurance, that it's constructed properly and everything is correct, let's say. It's sort of inspection, really, I'm talking about. Construction management, that's for new facilities. Plant commissioning, startup, that's new facilities. Validation activities, that's proving the design, the installation, and operation is correct. There's a sort of written rule or unwritten rule. If it's not written down, it hasn't happened. So if someone comes in and said, we've done this, okay, you sign a form saying you've done it and what you actually did and what tolerances you work to. And the last one is energy use and saving. There's a lot of energy used in making pharmaceuticals because of the airflows and the opportunities for heat recovery, a lot of air conditioning systems. Now, operating companies generally employ in-house staff and outsource new plant and equipment modifications to engineering contractors. And the mechanical engineers employed by operating companies are involved in plant maintenance and management and supervision of contractors, and for maintenance and the supervision of contracts of design and construction. And obviously there are opportunities with contractors, some very large engineering contractors to build pharmaceutical plants. So the roles are design engineers, which are covered. I talked about the facility, building services and utilities engineers. A lot of utilities, steam, water, air, etc. Project engineers, project managers, mechanical asset and reliability engineers. That's a sort of inspection. And I'll explain the particular work undertaken at a later date in a later presentation. the pharmaceutical industry has many successful and renowned international companies producing a wide variety of healthcare products. The larger companies, which you know about, GSK and Pfizer and all those, they are at the forefront with new products. When the product goes out of patents, there are companies that make the tablets or the particular drug out of patent, because when people are on a product, they probably are on it for the rest of their lives. So it's vital that the continuity is sustained, and the products are available. An obvious thing, but pharmaceutical companies benefit anyone in the world who requires treatment from these products. So if it works on me, it'll work on someone in Africa, and etc., etc. Finally, working in the pharmaceutical industry has given me the opportunity to make many new people travel and gain new experience and skills. I've gained a lot of experience with equipment, building services. I've done a lot of traveling in the United States, so I'd recommend it. It's a good industry to be in, and it's an ongoing. It's not going to disappear, let's say. So I'm going to hand over to John now. John?
I might take the reins back there, Maurice. Thanks a lot. Yeah. So,
I beg your pardon. Yeah. I may have to turn.
So I'll speak now about some key design documents. Our experts from the industries have shown you how each industry may have different facilities they design. Ultimately, we are facility designers, but one thing we do have in common are the design documents we see. So first, I'll very briefly talk about the process flow diagram. This is a PFD. What we see here is the principal process piping, denoted by the lines and arrows, and the major equipment and how they're connected. And you can see eventually what service they serve. This example appears to come. It is crude oil coming in. The top right, we have crude furnace export. And yeah, it just shows the major items, major recirculation systems as well. And that would differ from this next slide here, which is the PNID. So this is the piping and instrumentation diagram. This is similar in several regards. We still have major process piping. We still have major process equipment, but there's a greater emphasis on instrumentation and control here. So I've highlighted an example at the top right. If you see, we have a vessel called an accumulator there, and there is the line shows a process pipe eventually going to the flare. There's a valve downstream of that vessel, and it appears to be connected via what's a PC there, probably pressure control. Now, it's not my diagram here, but it's likely that on the accumulation of a certain amount of pressure, gas pressure at the top of that vessel, that instrument will tell that valve through the dotted line to open, which would then relieve that gas to flare. So that's what we see in the PNID. If you look below as well, we see an LCV. I've highlighted that in red, and that could be level control valve. So that valve would open or close or have some prearranged setting based on the level of liquid in that vessel. But yeah, all of us on this call should be familiar with that. This is something that we'd be seeing day in and day out and on jobs in the process industry. Next, what I have is, I'll try and be a bit quick. Feel free to ask questions in the box if you feel I'm going to rush through this next bit. But I've got an example here of what we do in practice. It's not necessarily chronological, but it does help to explain the situation in this format. So we start, let's say, with a site. We have this. We've got steel structure, some floors, and some nice birds in the back. Our next addition is the basic process plant. So now we've added a motor in blue, connected and coupled to a pump, likely a progressive cavity type, and piping to a vessel on the left and what appears to be a shell and tube heat exchanger on the right. This is the basic process plant. But to get there, we have to do a lot as mechanical engineers. As Masood had mentioned earlier, we are heavily involved with our piping team, who are mechanical engineers, with the 3D model and layout. So the distribution of equipment and piping and so forth is done by mechanical engineers. On the left, 3D model, you can see it's very, very complicated. And on the right is a plot plan. It's a primitive arrangement of where the equipment will go on the site. That is the responsibility of the mech engineer. As well as that, we'll also be reviewing vendor documentation. So it is not often that we will do the detailed design of each equipment. We will do the design of the facility. So we'll have, in this case, that pump vendor before. He will give us the information which will allow us to integrate that pump successfully with the rest of the facility. Some of the information we may pass on to other disciplines are, let's say, the piping nozzle loads, the allowable loads on each nozzle that's there at the top. On the right, we have connection details, so we know how big the nozzles are, where to connect them to, and what pressure rating they are. At the bottom, we have weights, so this would go to our civils department to ensure they can design the foundation correctly. And on the left, shown a quick foundation layout drawing, but it's for the anchor bolts, so we know it can be positioned correctly at site. I'll go next now and show you the value added by mechanical engineers. So for the motor, we have discussed with our electrical counterparts what the electrical loads will be. Foundation loads will be given to civil so they can adequately design the floor. Anchor bolt locations likewise so we can position it. And nozzle loads and sizes we've given to piping to make sure we don't bust the pipe. Next, we duplicate the rotating machinery. Now, I won't go into too much detail here, but in essence, rotating machinery is not as reliable as its static counterparts. So process-critical pumps and whatnot are often spared, which means you have one running, one standby. In event of failure, you can switch it over without shutting the entire process line down. Yeah, I'll leave it there for now. Then we move on to add the instruments and process control. And as you can see now, it's busy, right? We've got a lot more going on. We've got a lot of yellow piping, process control, depressurization systems. We've got some valves in there now as well, so we're not just running full throttle. We can control the system. And green appears to be the instrumentation here. So if I give you an example, if you look back to the P&ID we mentioned earlier, we had at the top there the pressure control on a valve, and at the bottom, level control on a valve. If we go back to this image, I can't say for sure what it is, but it's possible that that valve on the right, because I see a green instrument line come into it, that it will have some sort of control based off an instrument elsewhere on the plant. So the valves are shown there in yellow, the instrumentation shown in green, and it is possible, for example, that the level in that tank, in the vessel, will instruct that valve to perform a certain function. And that's how the P&ID will result in a material change in reality. So next we're on to fire protection and mechanical handling equipment. So the essential fire safety features are here. We've got a cabinet, some sprinklers and integrated piping. But as a mechanical engineer, something else you'll be involved with is the mechanical handling. Every item, valves, piping included, that requires maintenance, be it routine or during operation or anything at all, will require access, and ergonomic access at that. So here we've got some ladders on the right. We've got an unusual scaffold arrangement on the left, and as you can see, is likely poor ergonomic access. It's going to be a tough crouch job to get to some of those valves. The cranes are in there. Often this equipment is far too heavy to lift by hand. And if it's tucked away in a corner, you'll need to make sure that you can have the correct mechanical handling equipment, in this case a crane, to ensure you can access the items that need removing. It could be the tube bundle in the exchanger, it could be the motor, it could be the pump. But yeah, ergonomic and safe access to equipment that requires maintenance, that's within mechanical handling scope as well. So a quick before and after, just to show you, the level of detail and value added. Now, in the spirit of time, I'll make this brief, but my time, I've been here, 4 years in the process industry, and I have amassed, I think, sufficient experience to go ahead and now apply for the CEng. The process industry will cater to chartership applications. I've definitely felt that I've got the experience required. And for example, so if we take when I assess the suitability of perhaps different technologies for a duty, that could quite rightly come under A. Reviewing those vendor documents I showed you earlier, that general arrangement drawing, and specifying equipment as well, what fits the duty, that would come under B. Managing your vendors, this is something we do a lot in the mechanical industry, in the process industry as mechanical engineers, but yeah, vendor management would come under C. D is hit a lot. We have a considerable amount of discussions with our other disciplines. As I mentioned, it could be electrical, control systems, instrumentation, piping, civils. But yeah, a lot of communication. And on an engineering level as well, that's gone on. And lastly, to professional codes and standards or industry codes and standards as well, we have to meet, and legislative requirements too. Addressing those will meet the E-competency. So yeah, all in all, it's a safe bet. And lastly, just wanted to touch, before I open up to questions, talk about the future of the process industry. You may have heard the buzzwords for Industry 4.0 going around, essentially making a lot of process control and instrumentation without much human interaction. So the instruments we saw earlier, essentially getting smarter, probably smarter than me at this rate. And then the energy transition. So as, again, Masood touched on, we have diversifying work coming in. We're seeing production of battery technologies, so new batteries for electrical vehicles. We're seeing carbon capture come through and likely come in more and more, and hydrogen, of course, for the buzz that it has. There's a significant amount of infrastructure investment required. So these are the kind of projects we see coming in the future. And yeah, I'll open it up to questions now. Thanks a lot for listening.
Good morning, everybody. I've received 2 questions so far. One is from Zakaria Abdi, who asks, is this recorded and will it be available? The answers are yes, it is being recorded, and yes, it will be available, I believe, through YouTube, as was the last one. The second question is from Gaurav Nanajka, and he asks, let me do that properly. He noticed the heat required in making, for example, poppadoms is 170 degrees C. This heat is coming from natural gas stroke fossil fuels, or is it coming from the decarbonised process? I think the person to answer that might best be Penny Morton. Penny, for you.
Hello. In all honesty, I don't specialise in the poppadom process, so I have no idea. But something to bear in mind is, as some of the other speakers were speaking about before, was these processes which exist right now, there's a lot of ways that we can improve them in terms of for reducing emissions and carbon, but that is an area for innovation, and it's an area that the current industries are now trying to work towards, is changing the way that these machines or processes are powered to be a lot more sustainable. But there's a lot of teething issues to do that. It's not like we can just plug in and play a different system. There's a lot more mechanical engineering that needs to go on behind the process to make sure it's all safe, to make sure it's still going to run the same way. And that is where their innovation is working on today. So yeah, honest answer is I genuinely don't know, because I don't specialise in poppadoms.
Well, thank you anyway. Does anybody else on the panel have an answer to Gaurav's question?
I suppose I don't have a direct answer, but just to expand on Penny's point, the waste stream in one industry could be required in another industry, and there are innovative ideas going on and solutions going on where we can use that waste heat elsewhere. We need heat as well in the digestion process for waste. That waste heat is then used to heat water elsewhere on the site. You know, we're always thinking, all of us as our industry, where can that waste be used elsewhere? So it isn't truly a waste, and it can be to try and reduce our carbon. There's no point having waste heating one side and then heating water on another side of the plant. You know, we are trying to make everything stick together and make everything more sustainable and less carbon hungry. So just to add on to Penny's point.
Thank you, Pamela. I'd point out that the reason that an industry might regard a stream as waste, energy or otherwise, or useful, depends upon the design balance that is specified to start with. A long time ago, heat and energy were quite cheap, coming from coal or wherever, so you didn't bother, you just ditched the stuff to the atmosphere. Nowadays, the balance is partly cost, but partly environmental, and you will look, as Pamela has said, at using what would otherwise be regarded as waste. I have another question. This is from, well, it's not a question, sorry, this is Gordon Sharp of CPW. He's saying that it's a very interesting presentation and it was good to see a lot of potential crossover from mechanical building services, particularly on the fluor presentation. A question here from Jagadish Rao Balia from Shell. What is mechanical engineers' equipment design future in the hydrogen sector? I do not know who to pass that over to, apart from possibly Masood, please.
Yes, John, I think I can answer that. Right. So hydrogen, despite what we think, is nothing new. So we always knew about hydrogen and its use. In fact, for hundreds of years, not hundreds of years, for the past 50, 60 years at least, we've been using hydrogen in the refineries to enrich the diesel and petrol and to take the sulfur out. So hydrogen on its own is not unknown. It needs some specific design requirements because of the nature of the hydrogen, the small molecule size, and the potential metallurgical issues that may cause. Otherwise, everything is known and we're using it. What will the hydrogen expanding now in different sections, being different colors, we quote them now, blue, green, and they come from different sources. Ultimately, the mechanical design is very similar to what we had, but we are moving into high efficiency designs, which will impact all industries, including hydrogen. I hope that answers the question.
Thank you. Anybody else on the panel? Okay. Another question from Tosin Adedipe from Cranfield University. Can we find out a little more about Industry 4.0 in relation to process system project management? I've got to say the best source will be the IMechE headquarters website and follow the links from there. I could ask, Masood, do you have anything on Industry 4.0 off the top of your head?
Yes. So again, the key one on no, it's the same as any other industry. We are moving to like a data centric and processing data industry, which basically with the Industry 4.0, if you have enough data about the operation of, let's say, a piece of equipment or a plant or part of a plant, you can better run the plant and equipment, and also you can predict the maintenance requirements, which then it makes the process more efficient. And instead of waiting for something to break, you can repair it in time and extend life of the facility. So and this is coming in use everywhere, and with the increased use of, let's say, 5G, again, the communication between the different instruments and sensors you have and the data you can collect and process, all of that will move.
I've got a meeting at 1. I'll have something in the next 10 minutes.
So that's where we will see more use of that Industry 4.0.
Yeah, salad and whatever. Oh, do you want a salmon sandwich? Salmon, yeah, salmon.
Hello.
Sorry, thank you, Masood.
Could I just expand on that point?
Please do.
So actually at Koolmill, we have been working a lot on our IoT systems, and we actually just finished a 6-month project using augmented reality and HoloLens. So during COVID, we obviously couldn't get out to our machines, so we were using the Microsoft HoloLens to set up guides and essentially augmented reality instructions that we can then use out in the field. And this is going to reduce our costs massively so that we're not having to travel out every time to fix a machine. And then on the other side, we're starting to use, we've got our own dashboard. So essentially our machine out in India, if we want to change the speed, change the bell, or I can control that from my laptop here in Scotland. And we're working very much on the side of IoT, and there's a lot of other things to think about when working internationally with data. For example, in China, there's a lot of firewalls to be able to get through, and you've got to also think about whose data is this, who is responsible for it, and there's a lot of interesting new problems, potentially opportunities arising from Industry 4.0 as well. But there's a lot of great things that can come with it as well. If we can train up our engineers on the ground remotely, it means that experts in the field, we don't need as many of them. We can just have them communicate through technology on the ground and fix it in seconds compared to waiting for a flight over, which again is bad for the planet. So yeah, that's just something that Koolmill are working on as well.
Thanks, Penny. I'd point out that my reference before to design balance, the balance nowadays is very much towards the fact that you have available an enormous amount of data, materials, personnel, and so on, stress analysis and all the rest of it. To go to Penny's point in her presentation about beer can filling and saving a micromillimeter, you will have that data available and you can make those decisions. And it relies largely on the Internet of Things and communications connections, which are pretty readily available, apart obviously through Russia and China. So, do we have any more questions, please? Then, in that case, I can pass you back to Masood, I believe.
I think that will be ready to close the call.
Okay. Yeah, please do.
Guys. I think we'll close that out. All your questions seem to be answered. We're slightly over, but thanks a lot for participating. And yeah, hopefully we'll have future webinars in similar fashion, and you can join those as well. Thanks a lot for coming by.
Thank you all.